Okay, so this is my first attempt at a video, and you guys are the lucky ones that get to watch. So, what we're going to have a brief talk about is machines and frames. So, we are looking at chapter, I think it's 6.6, 6.6 in our text. It's what we've started this week. And so, specifically, what we are looking at is multi-force members. Okay, so what is a multi-force member? It's going to be made up of multiple pieces. So far, we have looked at simple systems, okay, where we have a cantilever, or we have a simply supported beam of some sort. It's simple, okay? A simply supported system is determinate in that we can determine the three unknowns that we have with our equilibrium equations, our three equilibrium equations. So a multi-force member is where we put several of these together and we connect them with a pin. Okay, so you can look in chapter 6 of your book and see some examples there, but we're going to walk through some of the examples and what do they look like and how do we tackle a problem. Okay, so when we look at multi-force members, we can have a frame. Okay, and a frame is usually what we're going to use to hold a load. So we might see a frame in a structure. Okay, and we're going to notice here we have two pins. And remember, at pins, we have X and Y forces develop because I can't pull this up and down or move it sideways like a skateboard would move, but this whole thing could rotate about the pin. Okay, so I have 1, 2, 3, 4 possible unknowns. And I only have 3 equilibrium equations. But because I have this internal pin, okay, that's going to provide me that extra equation I need. So I will have 3 of our equilibrium equations we've been using plus 1 pin. I now have 4 equations to tackle this problem, okay? When we look at a frame, we might also see beams. So we could have like some sort of a compound beam, and we could have pins in that as well, okay? The other thing would be a machine. And I know you all have seen machines. Many of you in construction have seen giant moving machines. This is going to have moving parts. So it could be as simple as a pair of pliers, or it could be a large crane that has many moving parts. It could be in a mechanical device. So you can also look in your book. We kind of have pulleys and examples in the book you can see of different types of machines. So if you'll notice back up here, I circled where we will have an internal pin. Okay, so we need to disassemble, and I can't spell. So let's go back and find my eraser, start over. Sorry about that. We need to I still can't spell. Hold on. We need to disassemble our multi-force member. Okay? When we disassemble our multi-force member, we cannot just cut it wherever we feel like it. I kind of think about it as if I had a workbench and I could lay this on my workbench and unscrew a screw to take it apart, that's where I would. Okay? So when we disassemble it, we're going to draw a free body diagram of each part. Okay, so we want to isolate. So what would a internal pin look like? So I went around the house and grabbed a few things. If you see inside here, there is a pin that is actually connecting the top to the bottom. Okay, so if I'm applying a force in we'll call this the X direction. I know I'm moving really fast, but if I were trying to pull this in the X direction, It doesn't go anywhere. Okay, so I'm putting a force on the lid, I'm pulling it in the X direction. The pin is transferring that force to the bottom case that I'm holding on to. Likewise, if I tried to move it in the Y direction, it's not going anywhere. Okay, so as I try to pull it towards me, see, I'm pushing it, my thumb is having to push back to keep it in place. This force is being transferred through the pin. So a pin can transfer X and Y forces. The second that I apply a force that causes rotation, rotation occurs. If we have rotation, we don't have a moment developing. Remember, forces only develop if we are resisting translation or resisting rotation. So that's a pin. Okay, where else would we have a pin? Like I said, I went around the house. Sorry for the examples, but here we go. Here's a Stein, and this one's pretty easy to see. So if I were to take apart this system at the pin, you can see I could unscrew the pin, I could lay the pin out on my paper, and I would have a top piece and a bottom piece. Okay, when I look at that pin, I'm going to try to go slow because I'm going too fast for the camera. If I try to pull this apart, the lid off the bottom part here, that pin is resisting that internal force, okay? So if I try to push the lid up and the Stein down, again, we're resisting the force in the X and Y direction, but we have rotation. Okay, that's going to be what this internal pin right here allows us to do. It's going to resist X and Y. It's going to transfer a normal force and a shear force, but it would allow rotation. Okay, I've got a couple more things. Okay, these are, let me grab these. So my daughter's sunglasses. How is the arm of the sunglasses put onto the front part of the frame? It's a pin. So when I cut this apart, this multi-force system, I am not just going to cut it willy-nilly where I feel like cutting it. I'm going to take a little tiny screwdriver, I'm going to take it apart there at the pin, and then I will lay out the earpiece and the front frame. Again, if I take this hand right here and I pull, okay, it's not going anywhere. I'm transferring that force in the X direction into the frame. If I try to push towards the back, if I try to push, again, this earpiece is not going anywhere. I'm transferring that Y force through the pen into the frame where I'm holding. If I apply a moment, I have rotation. So pins are going to have X and Y components. When we take them apart, when we draw a free body diagram, we only cut it at the pin and we're going to show X and Y forces. Okay, so then we're going to draw a free body diagram of each part. So we're isolating each part. Then we want to identify two force members. Do you all remember what a two force member is? It's what we've been working with in a truss. Okay, it's either going to be in tension or compression or, sorry, I'm a little crowded here. Okay, or we could have an angle that's supporting like a bracket, and because I don't have any other forces on here, I can recognize that the force will follow a vector line right through the holes. So I could actually break this up into X and Y components. If this bracket was a 4-inch by 4-inch bracket that I was using to hold shelves on the wall, okay, that would be a 1 square root of 2 angle. I would know that this X component is 1 over square root of 2 force, and the Y component was also 1 over square root of 2 force. And that way I can get rid of two unknowns, the X and the Y, and go back and just work with unknown force, okay? So a two force member, I mean, it could look like this. It's just going to be something that doesn't have any other forces on it except the end. It's going to be pulled or pushed, Okay, so we want to do that because that makes our job a little bit easier. It gets rid of some of the unknowns if we can call x as a function of f and y as a function of f. Okay, and then we are going to note where all of the pins are that we've taken apart. So I guess I'll go back and identify what we've identify, and we're going to look at pins. So if I have a very simple system here, okay, and this could be like the frame of my glasses and my hand on the, oh, you can't even see me. Sorry. If this could be like the frame of my glasses where I've got it pinned together, the earpiece on the frame. When I take this apart, I recognize, again, I have 2 pins, external. So I'm going to have 4 unknowns. Okay. I only have 3 equations. That's not enough. But I have that internal pin, which is going to allow me the extra equation I need for solution. So I can take it apart at that pin. I can just pretend I unscrewed it and it's now laying on my workbench. Okay. And I'm going to draw the internal transfer of force. So when I take apart the pin, I need to recognize if I'm pulling this way, I have to be pushing back so that we don't have any motion. We're in statics. The sum of our forces equals 0. If I'm trying to push down over here, this member is going to have to be pushing up equal and opposite so that we don't have motion. When I put these back together and I look overall, I don't see those forces. Okay, they're not there. They're internal only. So I have my overall free body diagram, and it is only going to have external reactions and forces. When I break it apart and I isolate each member, then I will have external forces and the forces on the pin. Okay, so I will work an example and I'll try to go slow through that example, but I'm hoping you can kind of see that we've started with this simple idea. We've already done that, and we're now moving into multi-force, which is a combination of frames and machines, so loads and moving parts. And we're going to disassemble that multi-force member. When we disassemble it, we can only take it apart where we could actually take our little screwdriver, unscrew it, and lay it out in parts on our workbench. Okay? We can't just cut it where we want to. That's not what we're doing yet. So we're going to isolate each part by unscrewing it in our minds and drawing a free body diagram of each part. We're going to identify any 2 force members because it just simplifies our job. Okay? And we are going to go from an overall free body diagram where we don't see the internal forces of the pin ever, 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 to our system taken apart, and we can represent that transfer of forces through our pin equal and opposite on the 2 sides of the beam. Okay, go check out my example.